In section 1.2, we're going to look at initial value problems. We are often interested in problems in which we seek a solution y of x to a differential equation that also satisfies some type of prescribed side conditions or oftentimes some initial conditions. So we'll have our differential equation, whatever nth order it is. So suppose we have an nth order differential equation, and we're subject to the following initial conditions. We want the value of the function solution to have a prescribed value at x naught. We want the first derivative to have some condition all the way up to the n minus first derivative. We want to have some kind of condition. If you were to think about kind of like going back to like calculus 2 or maybe even at the end of calculus 1, if you were to be able to solve a differential equation via integration, to undo n derivatives, you would have to do n antiderivatives. And therefore, every time you do an indefinite integral, you get a constant of integration. And so to be able to find an explicit solution or a particular solution, we would need to solve for all of those constants of integration. And that's kind of like what these initial conditions would give us, is that extra information so that we can precisely describe the particular solution from the family of solutions. So these y sub zeros, y sub ones, these are all numbers, by the way. These are going to be constants. And we call this the nth order initial value problem. Oftentimes we'll just kind of abbreviate it very briefly as the IVP. So it's just a differential equation with some initial values that we want to be satisfied by our solution. In the cases of n equals to 1 and n equals to 2, for example, if we had a first order differential equation, we would want to have one initial value, which would be the function at x naught. If we had a second order differential equation, then the initial value problem, we would want to have a condition on the initial value of the function as well as its derivative. These two problems are kind of easy to interpret geometrically. What we're looking for is a solution y of x that solves y prime equals to f of x comma y on an interval I that also contains x naught, so that its graph passes through the specific point x naught kind of y naught. Okay. So here's kind of, you can see what it would look like for a solution of a first order IVP. We have this kind of family of solutions, and the particular solution we would get would be the one that satisfies the initial value, which would be this curve in blue. Okay. If we also wanted to look at kind of geometrically what would be the interpretation of a second order initial value problem, well, again, we want to find the solution curve. So out of all of this family of solutions that we get, we want the one that, first of all, would have the initial value that we wanted. And in addition to that, that curve has to have this slope. In other words, the first derivative, this condition right here, the slope of the solution curve at that point has to have the prescribed slope, which is what we see right here. Let's look at some explicit examples of this. For instance, let's suppose that we had the function y equals ce of x. And we know that this is a family of functions. It's defined by a parameter c. That's going to be defined on the interval from negative infinity to positive infinity, because that's the domain of e to the x. Let's also suppose that we wanted y of 0 to be equal to 3. So here's what we have. We have y equals c e to the x. And for the initial condition, if they want y of 0 to be equal to 3, then this gives us information that allows us to solve for the particular value of the constant. What we can do is everywhere I see an x, I can replace it with 0. And then the resulting function value should be 3. So this would give us 3 equals c times e to the 0 is 1, or 3 equals 2 to c. So this particular solution in this case would be y equals 3 e to the x. We could also instead have had it such that the initial point could have been 1 comma negative 2. Let's see what that would have looked like. So this differential equation, by the way, I didn't write it out, but this would be dy dx equals y was the differential equation, and now they're asking for y of, I think, 1 to be equal to negative 2. Let me just quickly check that. Yep, y of 1 to be negative 2. Let's go ahead and solve that. So we know that the solutions was solved earlier. It's going to be c e to the x. With this particular solution, I can plug in 1 for x, and we should get out c. To solve for c, we can just divide both sides by e, so we get negative 2 over e equals to c. So our particular solution in this case would be y equals negative 2 divided by e times e to the x. And if you compare this against what's written in the textbook, they write it a little bit differently. We can kind of combine the e terms. This e that's in the denominator, you can bring it up to the negative first power. And now this is simply multiplication by like bases, so we can add the exponents. X plus negative 1, we can write as e to the x minus 1. So this function satisfies this first order initial value problem. It's a function whose derivative is equal to itself, and if we evaluate the function at 1, we get the value negative 2. Here we can kind of see the family of solution curves for that last example. Here is our particular solution that satisfied the initial value 0.03. Here would be the solution curve that would satisfy 1, negative 2. One of the things that's going to be extremely important to kind of focus on is the interval I of definition of a solution. So whenever we create solutions to these differential equations, it's always kind of fair to ask, well, on what intervals are our solutions defined? For example, we're not going to show this, but just take it for a fact, or you can check it on your own, that this family of solutions, y equals 1 divided by x squared plus c, indeed solves this differential equation, y prime plus 2x y squared equals to 0. If we want the initial condition y of 0 to be equal to negative 1, then that would allow us to go ahead and solve for c. Let's actually do that on this one. So we have 1 divided by x squared plus c, and we want y of 0 to be negative 1. So I can plug in 0 for x, and the output we should get should be negative 1 over there. So we have negative 1 equals 1 over c. Cross multiply, divide, reciprocate both sides. Either way you slice it, this should give us the value c equals 2 to negative 1. So we get this function, y equals 1 divided by x squared minus 1. Now the question then becomes, well, on what intervals is this thing defined? From pre-calc, if you go back and find the domain of this function, we cannot have the denominator be equal to 0, which means that x squared cannot be 1, and then taking square roots, it means that x cannot be equal to plus or minus 1. So on a number line, we can't use negative 1, we can't use positive 1, but any other values of x would work. So as a function, the domain of definition for this thing would be as follows. You have negative infinity to negative 1, union negative 1 to 1, union 1 to infinity. Let's now kind of talk about what that would mean for our differential equation. So again, as a function, the domain of a function would be all values of x except -1, and +1. And if we wanted to, we could kind of see what the graph looks like. When x is -1 and x is +1, at those values, we're going to have vertical asymptotes. Now, if we consider this as a solution of the differential equation, the interval I of the definition for this function could be any interval over which y of x is defined and differentiable. We see that those intervals of definition were the three that we kind of picked apart a moment ago. It's defined from -infinity up to, but not including -1. It's defined between -1 and 1. And it's also defined from 1 to infinity. So we could think of that function as a solution to the differential equation on any one of those three intervals. Furthermore, if we think about it in terms of like an initial value problem, if we take the initial value y of 0 equals to -1, then the interval I of solution for that differential equation should be the largest interval in which the initial value point exists and in which the function is defined. If we come back up here, that's kind of like the three branches that we see here. That initial point, 0, -1, would be a point right here, which would be the portion of that curve in between -1 to 1. So we would think of this function as being a solution to this differential equation over the interval -1 to 1, because that's the largest interval where the solution is defined and includes the initial point. Let's take a look at another example of a initial value problem. This time, let's take a look at this particular differential equation. We have the second derivative of x plus 16 times x is equal to 0. And they're claiming, they tell us up front, that this expression, x equals c1 cosine 4t plus c2 sine 4t, is a two-parameter family of solutions to this differential equation. Let's see if we can find the solution to the initial value problem such that x of pi over 2 is equal to -2 and x prime of pi over 2 is equal to 1. So we have y equals c1 cosine 4t. Actually, it should be x. So it should be super picky. This is x equals, and then plus c2 sine 4t, and then they give us an initial condition at pi over 2 and an initial condition on the derivative, the first derivative, also at pi over 2. They wanted x of pi over 2 to be -2 and x prime of pi over 2 to be equal to 1. So -2 and 1. Let's go ahead and, first of all, let's look at this initial condition right here. If we plug pi over 2 into this function, that's going to give us c1 times the cosine of 4 times pi over 2 plus c2 times the sine of 4 times pi over 2. That value should be -2. This is going to tell us that c1 times the cosine of, this is going to be 2 pi, plus c2 times the sine of 2 pi equals -2. The cosine of 2 pi is 1, so that's c1 times 1, which is c1. Sine of 2 pi is 0, so it's become 0 times c2 equals -2 c2, and that tells us that the value for c1 is going to be -2. We also need to find C2, and we can do that with the second condition. Now that I know the value for C1, I can go ahead and plug it in to be a little more explicit. So right now we know this. We know that x equals -2 cosine of 4t plus C2 sine of 4t. Let's take the derivative. X prime is going to be equal to, here you're going to have to use the chain rule. Derivative of cosine is negative sine, and you're going to have from the chain rule 4 coming out as a multiplying factor. So this is going to end up being 8 sine 4t for the derivative. Here we're going to get plus derivative of sine is cosine. You're also going to have a chain rule. So we have a factor of 4 coming out. We get this. Let's now evaluate the derivative at pi over 2. X prime evaluated at pi over 2. This is going to be 8 times the sine of 4 times pi over 2 plus, and I dropped my C2 there. We have 4 C2 times the sine of 4 times pi over 2. Actually, copy mistake, sorry. We better not have a sign there. That's cosine of 4 times pi over 2. And let's see what we get. So this expression is supposed to be equal to 1. So we have 8 times the sine of 2 pi plus 4c2 times the cosine of 2 pi equals to 1. Sine of 2 pi is 0. Cosine of 2 pi is 1. So we find that 4c2 equals to 1. Divide both sides by 4. So the value for C2 would be 1/4. So this gives us our solution to the initial value problem. The constant C1 should be -2. So it's -2 cosine of 4t, and the value for C2 should be 1/4. And now this is a family of, this is a solution. It's a function such that it solves the initial differential equation and satisfies our initial values. One of the next things that's going to be extremely important, especially in an ODE class, is existence and uniqueness of solutions. The problem and the question of existence is, does the equation actually have a solution? Do there exist solutions to these differential equations that we're looking at? And then the follow-up question would be that if the answer is affirmative, if there is a solution to the differential equation, then the next question is, well, is the solution unique, or are there other solutions that are out there? So existence and uniqueness is something that sometimes kind of gets taken for granted. We will almost exclusively work on ones that do have a solution, because otherwise it's kind of boring. There's not much you can do. But when faced with a brand new differential equation for the first time, existence is something that should certainly be asked. And then uniqueness will play a fundamental role. We'll be working with that all the time in making sure that we come up with the most general solution to our equations. As an example to kind of illustrate this, if we had the differential equation dy dx equals x times y to the 1/2 power, it is the case that y equals 1/6 x to the 4th would satisfy that differential equation, but so too would the constant function y equals to 0. Okay. Furthermore, both of them satisfy the initial value problem, dy dx equals x to the y to the 1/2, and the initial condition y of 0 equals to 0. So for this function, not only does it have a solution, so solutions exist for this differential equation, furthermore, they're not unique because we have two solutions. One is the constant function y equals to 0, The other would be the constant function y equals 1/16 x to the fourth.